everyone. Thanks for tuning in. This lecture video is going to be focusing on section 5.2 of the textbook, which is limits of finite sums and area. And so we're actually, because I've sort of scaled back the course in terms of the content, we're not actually going to focus too much on the limit portion of this section. I'm just going to kind of give you a very scaled down version of what summation notation is, and this idea there's this term called a Riemann sum. So we're going to talk about what that is, and then we're going to sort of relate it to this approximation of the area underneath the curve. So if you remember in section 5.1, in our last section that we covered, we were using rectangles to approximate the area between a function and the x-axis. And we saw three different techniques for how we determine the height of the rectangle. And so that was either by using the left endpoint of a subinterval, the right endpoint of a subinterval, or the midpoint of a subinterval. And so that was the method we saw. And that's actually not the only way that we can approximate area. In fact, sometimes you'll see people using parabolas to approximate the area. Sometimes you'll see people using other shapes like trapezoids. But for this course, we focus mostly on the rectangles. The other thing we saw was how to relate the area under the velocity curve to the distance function, which is its antiderivative. So we saw this relationship between area and antiderivatives, which was pretty interesting, and we're going to continue to explore that today. So what we know so far, oops, already, just ignore the line that I wrote through. One day I'll get used to this. Okay, so what we know so far is that we can use rectangles to approximate area. We know that the more rectangles that we use, the better the approximation will be. So if you have an interval of length 5 and you only have 5 rectangles, okay, well there they all have nice base length, they're all going to have base length 1, but your approximation may not be great. But if you did something like 15 or 20 rectangles, it would be a pain in the butt, but your approximation would be much better. Finally, we know that if we add up the area of all the rectangles, we will get our approximation for the area under the curve. So we're now going to see some new notation, which is just going to help us express the addition of these areas of rectangles. And so the notation we're going to see is something that is used in place of a whole bunch of plus signs. So when you're adding up a whole bunch of things, that can be really long to write out. Imagine you wanted to add up 100 numbers. Rather than having to write out, 1 plus 2 plus 3, we have this condensed notation that we use, which is called sigma notation, and it's going to help us express this. And so one of the reasons that I kept this sigma notation in the course is because if you continue on into Math 101, there's a unit in Chapter 10 called Sequences and Series, and for series specifically, you're going to be using the sigma notation constantly. So I wanted to make sure that you guys did see this notation in this course. So the sigma notation, I'm going to write it out for you. So it's a Greek letter sigma, and we use the capital letter sigma. So let me just try to do this here. So it looks kind of like this. There we go. That's actually pretty good. I'm impressed with myself. And so on the sigma on the top, there's usually some sort of number or letter, and then on the bottom you have this thing called an index, and I'm going to define what these things are in a moment. So this is sort of what our expression would look like. I'm going to put a little a sub I here. Okay, so on the top, this n here that's on top of my sigma letter, this is telling us the last value that I will take. So this is the last value of I. This is the last value of I. And then on the bottom, this I equals 1, this is actually telling us what the first value of I is. So it could be I equals 5, which tells you that the first value of I is going to be 5. But here I'm saying I equals 1. So this is, whatever number is on the bottom, this is going to be your first value. So this is the first value of I. And so what ends up happening, I'm trying to get the dot on the I, there we go. What ends up happening is that you start at whatever value of I is on the bottom, and you keep increasing by 1, by integers of 1, until you get to the top value. So imagine that this was I equals 2 to 4. So if that n value on the top was actually a 4, and on the bottom we had I equals 2, then you would cycle through I equals 2, 3, and 4, and you would stop at 4 because that's the top value. So that's what this bottom number and this top number mean, is it's telling you sort of what number you start at and what number you finish at, and then you do all of the numbers in between, increasing by 1 each time. And so this term AI, this is actually what you're going to be, plugging your I values into. So if I is going from, 2 to 4, you would be plugging in I equals 2, I equals 3, and I equals 4 into this function here, AI. So here, maybe I'll just write out what this would look like. So if we have the sum of the AIs as I goes from 1 to n, what that means is we'd start off with A1, so plugging in I equals 1 in for I. And then the sigma symbol actually means that we're adding these. So this is actually, we're adding A1 plus, now we've already done I equals 1, so next we would do I equals 2. So that would be A2 plus, and you would keep doing this, so plus A3 and so on, A3. And we would keep doing it, so plus dot dot dot, it's hard to do dots with a stylus pen, until you get to the last value of I, which is n, so all the way up to plus an. So if I were to sort of describe this, I'd say that you keep adding each AI term as I goes from 1 to n. So you add the AI terms from I equals 1 to n. So that's really what this sigma notation is telling us to do. So let's work through a couple examples and it'll make this notation really clear. So in the first example, we have this sum symbol. So it's the sum from k equals 2 to 6 of k minus 1 squared. So this k minus 1 squared, this is our function that we're going to be plugging in k equals 2, 3, 4, 5, and 6 into. And in between each time that we plug in the value, we put a plus sign. So we're adding all of these terms. So if I were to rewrite this, okay, well first, my first value of k is 2. So I'm going to plug in k equals 2 into my function. So that's 2 minus 1 squared. Then, so now k doesn't need to equal 2 anymore because I've already plugged it in. So now k equals 3, and I want to put a plus sign in between each term. So it's 2 minus 1 squared plus, now k is equal to 3, so we have 3 minus 1 squared. Plus, and then we keep going until k equals 6. So this is k equals 2. This is k equals 3. So I still need to keep going. So k equals 4. I'm going to have 4 minus 1 squared plus, now k equals 5. So 5 minus 1 squared plus, and finally my last term is k equals 6. So 6 minus 1 squared. So this last term here is the k equals 6 term. And so we know that we stop when k equals 6 because that's the top number on our sum symbol. So then all that's left to do is just work out what this is. So this is going to be, so 2 minus 1 squared is 1. So it's 1 plus 4 plus 9 plus 16 plus 25. And so we end up with 55. And so why do we use this notation? Well, if you look on the left-hand side where we have the sum symbol from k equals 2 to 6 of k minus 1 squared, that is equivalent to the expression that is immediately to its right. So this 2 minus 1 squared plus 3 minus 1 squared plus 4 minus 1 squared and so on, that expression is exactly the same as the one that's on the other side of the equal sign. And so we see that that expression on the left is just a lot more condensed. It's a lot smaller. And you can imagine if you had something like 50 terms, you would not want to write the addition of 50 terms. So we often use sigma notation just to condense our sums. So it just takes up less space. So let's work through another example. So here it's a little bit more abstract. We don't actually have the function. It's just arbitrary. It's f of xk. And so we are not going to be able to figure out a numerical answer like we did in the previous example. But that's okay. We just want to sort of cycle through the plugging in and what this sum symbol actually means. So this one in example 2 is saying we start from k equals 1 and we go all the way up to k equals 7. So 1, 2, 3, 4, 5, 6, 7. And when we're plugging in for k, well, there's really only one spot where k appears. It's a subscript of our x. So that's all we're going to be able to plug into. So we'll have f. So we start off with k equals 1, so we'll have f of x1 plus, now k is equal to 2, so that's going to be f of x2 plus, and we just keep going until we get to 7. So f of x3 plus f of x4 and so forth, plus f of x5, I know this is kind of tedious, plus f of x6, and last but not least, our final term when k is equal to 7 is f of x7. And we don't know what f is, so we have to leave it like that. But that would be what that sum symbol is expressing is exactly what I've written down. So, you know, rather than writing down these 7 terms, you could write down the single term and it means the same thing. Okay, so then the natural question is, how can we connect this sigma notation to area under the curve? Well, if you remember when we were doing area under the curve, we were just adding up a whole bunch of rectangles, areas. And so this sigma notation allows us to condense addition. And so since we're adding up a bunch of areas, we can use the sigma notation to represent this. So our answer is that we need to approximate, we need to write our approximations, so our addition of these areas, using the sigma notation. And we're going to use an example to sort of illustrate this. So the first example we have here, suppose we have a function f of x, and we want to approximate the area under the curve on the interval 1 to 8. And we're going to do this using an arbitrary number of rectangles, so we'll say n rectangles. So the first question is, what is the base length of each rectangle? And so if we remember the first step, we want to evenly divide the interval so our interval is 1 to 8 into n pieces. So the key is we want the base length of each rectangle to be the same, so we divide our interval into the equal size pieces. So how big is each piece going to be? Well, how long is our interval? Our interval goes from 1 to 8, so it has length 7. So we're going to take 7 and we're going to divide it into n equal pieces. So that's going to be 7 divided by n. So each piece is of length 7 divided by n. And another way to think about it, so how did I come up with the number 7? Well, I found the length of the interval. How do you find the length of an interval from 1 to 8? I mean, this one's pretty easy. You can just do it in your head. But really what we're doing is we're using subtraction, right? We're taking the bigger number, 8, and then we're subtracting the smaller number, 1. So it's actually, you can think of it as 8 minus 1 over n, and this will make more sense in a little bit here why I'm writing it that way. So either way, though, we can say that our base length, b, is going to equal to 7 over n. Okay, so then the next question is a little bit trickier. If we're using right endpoint approximation, what is the height of each rectangle going to be? So in order to figure this out, let's draw a little bit of a number line here. Okay, so our number line starts at 1 and it goes to 8. And I'm just going to try to do my best of drawing, n equal pieces. Of course, we don't know what n is, so I'm going to put a dot, dot, dot there. Okay, so there's some arbitrary amount of pieces that we are cutting this interval into, and so we have, x1 and x2 and so on. So I'm using the right endpoint, right? So my first subinterval is going from 1 to this first tick mark. And so of the two endpoints, I'm going to use the right one. So that's why I'm labeling that endpoint x1, because that's going to be the endpoint that we use. And then x2 in the next subinterval between x1 and x2, I would use the endpoint x2, because that is the right endpoint out of the two of them. So we keep going until, I'm going to call this one down here xi, because I don't actually know what it's equal to. And so let's try to think about this. Well, the distance between each subinterval, the length of each subinterval, we just said is 7 over n. I'm going to try writing that again because that is hard to read. So yeah, our distance is 7 over n. And so if I wanted to get to x1, what would that value be? Well, it would be 1 plus 7 over n. So this guy here is 1 plus 7 over n. If I wanted, it's really hard for me to draw an n. If I wanted to get to x2, then I would have to go from 1 plus 2 7 over n's, right? So to get to x2, and I don't really have space to write this, so I'm going to draw a big arrow. To get to x2, that's going to be 1 plus 2 times 7 over n's, because we need to do two little spaces to get to the second point. So if I wanted to get to xi, I'm going to have to go 1 plus I 7 over n's. So this is 1 plus I times 7 over n. So, okay, why is that helpful? Why did I care about what these endpoints are? Well, if you remember, how do we determine the height of our rectangles? The way that we do this is we take whatever endpoint and we plug it into our function to find the y value of the function at that endpoint. So the endpoint is what is the x value that we're plugging into the function to get the y value, which is our height. So if we don't actually know what the x value is, we can't find the y value because we're unable to plug anything into the function. So this is why we needed to actually figure out, how do you find that x value, that xi? We know it's somewhere between 1 and 8, but what specifically is it? Well, it's going to be 1, so the first point in my interval, plus I times the distance of each little subinterval. So that's going to be the x value. So if I want to find my height, if we want to call it hi, my height of my rectangle is going to be my function f evaluated at xi, right? If we're going to take that ith endpoint and we're going to plug it into our function. And so we actually can be more specific than that. That's going to be f of this 1 plus I times 7 over n, which I'm just going to write in a little bit more simplified way. So that's 7i over n. So we would take 1 plus 7i over n and plug that x value into our function in order to determine the y value. So then if we piece this all together, the approximate area under the curve between 1 and 8 is going to be, so we know our area, we're just adding up n areas of rectangles. So it's going to be base times height 1 plus base times height 2 plus so forth until we get to base times height n, right? So it's the height of these n rectangles, the area of these n rectangles that we want to add up. And so what we see here is that we have the sum of n things. And so we can use the sigma notation to just condense it a little bit more. So this is going to be the sum, and we have to try to figure out how to index this. So what we see here is that these h's are the only things that are changing, right? The base length of our rectangles is the same for every single rectangle, so it doesn't change. But these h's, we go from h1 to h2 to h3 all the way up to hn. And so we can see that our index is starting from 1 and it's going all the way up to n. So on the bottom we're going to say I starts off equaling 1 and it finishes when it equals n. And so what are we going through each time? We're doing the area of the rectangle each time. So it's base times height I. So those two expressions are actually the exact same. And now all we can do to sort of be even more specific here is we can rewrite this in terms of what the base length actually is and what the height actually is. So our base length is this 7 over n. That's the base length of each rectangle. And our height is going to be the y values of the function at the right endpoint. So it's going to be 1 plus 7i over n plugged into our function f. So f of 1 plus 7i over n. So that there gives us an approximation using n rectangles for the area under the sum curve f of x. Now, if we are using left endpoints, what are the heights going to be? So remember, if we use left endpoints, the base length isn't going to change, but the height will. So now if we were to draw the same interval again, so going from 1 to 8, and we were to chop it into n arbitrary pieces, all of equal size, then now the left endpoint that we're using, well, the first endpoint is actually going to be at 1. So that's going to be our x1. The next tick mark will be x2 and x3 and so on. And so then we'll call this one xi. So if we want to figure out, what is that ith endpoint going to be, well, again, we know that the distance between each subinterval is 7 over n. And so if we want to get to the ith one, well, let's think about what it takes to get to x2. x2 is going to be 1 plus 1 times 7 over n. x3 is going to be 1 plus 2 7 over n's because it's 2 tick marks away. x4 would be 1 plus 3 times 7 over n. And so what we see is that if I'm at x4, I go 3 tick marks. If I'm at x2, I go 1 tick mark. So if I'm at xi, I'm going to go I minus 1 tick marks away. So this xi is actually going to be 1 plus I minus 1 times 7 over n. You always go 1 less because we actually started at the left endpoint this time. So that means that our ith height, hi, which is always going to be f at xi, is equal to f of 1 plus I minus 1 times 7 over n. So we're taking that x value and plugging it into our function to find the y value. So then putting this all together, just like we did for the right endpoint approximation, we end up getting that our approximate area, which even when we're using the left endpoint approximation method, it still has the same idea of adding up n areas of rectangles. So it's base times height 1 plus base times height 2 plus base times height 3 and so on until we get to the base times height n. So that's the area of n rectangles that we're adding up there. We can use our sigma notation to represent this. So we start off at 1 and we go up to the nth rectangle. And so we have base times height I. That's our condensed way of writing this using the sum notation. And then just plugging in for what our base length is and our height is. Well, our base length didn't change. That's still 7 over n. So that's the same as the last question. But our ith height is going to be the function evaluated at the left endpoint, which is 1 plus I minus 1 times 7 over n. So we have f of that as our height. Okay, so this looks pretty gross, and it's probably just easier for you to write out the areas of all of those rectangles and then add them up, and that's fine. But the reason that I wanted you to see this is because we're going to be introduced to something called the Riemann sum. And the Riemann sum looks exactly like this structure here. So for you to recognize it as just a whole bunch of areas of rectangles, it's important to first write it out this way. So there's a couple things to note first. So one thing to note, and we kind of talked about it in section 5.1, but we didn't necessarily see an example of it. So since we are using the function values as the heights, so we get the heights of each rectangle from the function, this means that what we are finding is something called the signed area under the curve. So you can imagine that if the y values fell below the x-axis, if they were negative, what would end up happening is that we would get negative area. And so that's actually allowed. So what we call it is the signed area, because sometimes it will be negative. So let's just make a note of that here. So negative y values so these are the ones that fall below the x-axis. These are going to give us negative area. So we'll give us negative area. And that's because the height of our rectangles is going to be a negative number. And so we allow for negative area when we're talking about the area under the curve. We're actually talking about the signed area. We just normally don't say the word signed, but that is in fact what it is. So you may get some negative values sometimes, and that's okay. Eventually, in I think the next section, we're going to talk about something called total area. And so that when we're talking about total area, we actually don't want it to be negative. And so we will learn ways to deal with that. But for now, it is okay for us to get negative area. Okay, so in general, let's write a sort of a general formula. If we want to approximate the area under an arbitrary curve f of x on an arbitrary interval a to b using n rectangles, the way that we would do this is, so just like we wrote out before, but we just have to generalize our formula here. So we know that we're going to be adding up n rectangles. So I is going to go from 1 to n. And we know that it's going to be base times height, because that is the area of a rectangle. So the question becomes, well, what's the base length and what's the height when we don't actually know what the function is and we don't actually know what the interval is? And so how do we find the base length of the interval? Well, I'm just going to actually scroll up so that we can go back to where we found the base length on the specific interval. So when the interval was 1 to 8, we knew the base length was 7 over n. And the way that we computed this is we took the length of the interval, which was 8 minus 1, and we divided it into n pieces. So this 8 minus 1, we took the last value in the interval and we subtracted the first value in the interval. That's how you can determine the length of the interval. And then we divide it by n because we're using n rectangles. So we're chopping our interval into n equal pieces. So if we now don't know the specific values in the interval, we just know it's a to b, the way that we find the base length is we take b minus a, so that's how you find the length of the interval. You take the last value in the interval minus the first one, and you divide it into n pieces. So that's going to be our base length. Now for our height, again, let's scroll up and look at our left endpoint height here. We see that it was 1 plus I minus 1 times 7 over n. Well, let's figure out what each piece was. This 1 was the first value in our interval. So in our more general example, that's going to be an A. This I minus 1 is how many jumps we had to make to get to the left endpoint. And so that's going to stay the same. We're still using a left endpoint approximation here. The 7 over n, that's just our base length, the length of each interval. So This 7 over n we already figured out is b minus a over n. So to rewrite this, it's going to become a plus I minus 1 times b minus a over n. So I'm going to try to fit this here. It's going to be a little bit squishy. So actually maybe I'm going to write it just a little bit below, but it belongs up here. So it's going to be f of a plus I minus 1 times b minus a over n. So that's the more general way of writing the height of a left endpoint, is we're plugging in a plus I minus 1 times b minus a over n into our function to find its y value. So same idea when we want to find the area using the right endpoint. We're just generalizing the exact formula that we came up with in the above example. And so we end up with the area being approximately the sum from I equals 1 to n of, well, our base length is still the same, so b minus a over n. And our height is almost exactly the same, except instead of having to take I minus 1 jumps to get to the left endpoint, we have to go one more jump. So I jumps to get to the right endpoint. So it's going to be f of a plus I times b minus a over n. Okay. So it would be fair if at this point you felt like this was kind of strange. But if we just look at the next page here, we have some new terminology to introduce. So we have a special name for these types of sums. So when we're adding up the areas of the rectangles, this is actually called something. So these are called Riemann sums. There was a famous mathematician named Riemann, and this is why these sums are named after him. So he worked a lot with approximating the area under the curve. And so the general form for a Riemann sum is the sum, so they like to use k's, we used i's, but it doesn't really matter. So it's the sum from k equals 1 to n of f of ck times this thing called delta k. So ck is going to represent the type of endpoint that we use. So ck could be a left endpoint, a right endpoint, or the midpoint, so the three methods that we saw. F of ck is then going to be the height of each of our rectangle, and this delta k that they use there, that triangle is a delta. So delta k is the base length of each rectangle. So if we just sort of highlight it here, we've got this f of ck as our height, and this delta k is our base length. So it really is just adding up the areas of rectangles, base times height. So an example to work through, and we're not going to focus too much on this, so I will say right here, Riemann sums, I'm not going to be testing you on the Riemann sums. I will be testing you on the sum notation, because you do need that for Math 101. And the reason why I'm introducing Riemann sums is because it's going to help us relate it back to antiderivatives and the integral. So it is important to see it. So for this example, we want to find the Riemann sum, which approximates the area under the curve f of x equals 2x squared plus 7x plus 1. And we're doing this on the interval 2 to 5. And we're letting ck be the right endpoint approximation. So the first thing that I like to do is I like to draw out the interval 2 to 5. And we're going to break it into n arbitrary pieces. So I'm just going to write some tick marks. Okay, so these are n equal pieces. And we know, well, how can we find the distance, the length of each piece? So this base length we know is equal to b minus a over n. That's the general form for it. Well, what is the length of our interval? We're going to do 5 minus 2 divided by n, so that's 3 over n. So each subinterval is of length 3 over n, and we're using the right endpoint of each subinterval. So on the first subinterval, we have 2 to this value, which we'll call x1, and we would use x1 as our endpoint because it's the right one. On the subinterval x1 to x2, we would use x2 as our endpoint. And so I'll call this one over here xi. And so we know that to get to xi, we're going to start at 2, and then we're going to add I jumps. So I jumps of length 3 over n. So that is actually what xi is equal to. So if I wanted to find the height, well, my height of a rectangle is going to be f evaluated at xi, and we know that xi is actually 2 plus I times 3 over n. So we're going to take that value and plug it into our function. Well, in this question, we actually happen to know what the function is, right? So we can actually plug it into this 2x squared plus 7x plus 1. And so what we get is, it's kind of ugly, we get 2 times 2 plus I times 3 over n squared plus 7 times 2 plus I times 3 over n plus 1. So everywhere we see an x in our function, we're plugging in the value xi, which is that really gross looking thing, the 2 plus I times 3 over n. So that gets plugged in everywhere. Okay, so then we know our base length, we know our height, so we can find the area of these rectangles. We just have to multiply them together. So if I want to actually write out what the Riemann sum is, this Sn, it's going to be the sum from I equals 1 to n, because we're adding up n rectangles, and it's going to be this height, which is 2 times this really gross expression here, times I times 3 over n all squared, plus 7 times 2 plus I times 3 over n plus 1. So then I'm going to close that with a big square bracket. So that's just our height there. And we need to multiply it by its base length, which is just 3 over n. So the base length isn't too bad. So that's our base length. So that is the expanded Riemann sum. Okay, so the main point to make about these Riemann sums is that the more rectangles that we have, the more accurate our approximation is going to be. So our Riemann sum Sn represents the approximation of the area under the curve using n rectangles, but we know that if we use more rectangles, our approximation is just going to keep getting better. So if we wanted to actually get the exact area under the curve, if we didn't want it to just be a rough approximation, we would have to use infinitely many rectangles in order to do this. And so what we would need to do is actually allow the number of rectangles n to go to infinity. And so how do we do this? Well, we use limits. So this is connecting back to the beginning of the course. We actually can represent this area under the curve as a limit of the Riemann sum. So the exact area under the curve, f of x, on an interval a to b, can be found by taking the limit as the number of rectangles goes to infinity. So our area exactly equals the limit as n goes to infinity of this Sn, of this Riemann sum. So let's rewrite that as the limit as n goes to infinity of the sum from I equals 1 to n of our rectangle's area. So this is f of xi times whatever our base length is, so we'll call it delta I. Okay, so if we had not scaled back on this course and been able to go through the entire course, what we would have done with this is we actually would have learned how to take the limit of these sums. So how do you take the limit as n goes to infinity of a sum? And so we would have learned sort of these properties of the sum, which allows us to get rid of the sum symbol and then take its limit. And it's pretty interesting, and if you look in the textbook, you can look at some examples of this if you are interested, or please feel free to email me if you want to talk about this more, because I do have some notes on this, but we decided just to cut back on this myself and the Math 100 instructor decided that you don't really need to know this in order to do well in Math 101. It doesn't really come up again. But it is a nice way of sort of seeing how to find the area under the curve. And what there is actually a nice analogy with derivatives. So if you remember at the beginning when we learned derivatives, we actually figured out that the derivative is defined as a limit. So we had this long limit definition of the derivative, which allowed us to find the derivative using limits. And then afterwards we learned quick rules for the derivative, and that allowed us to not have to use the limits anymore. Well, with the antiderivative, with the integral, which we're going to define in the next section, it's the same thing. It's actually defined in terms of a limit of these areas of rectangles. And just like there's a long way to find the limit of the derivative and then a short way to find the derivative, it's the same thing with integrals. So the long way is to take the limit of these Riemann sums, and then we're going to be learning the short way using antiderivative rules. So there's just two more notes to make before the end of this section. So the first note is that since we are using infinitely many rectangles to find the exact area, it does not matter what type of approximation we use to find the heights of these rectangles. So that means it doesn't matter if you use the left endpoint, the right endpoint, or the midpoint. It's the same difference because there's infinitely many rectangles that you're using. So the endpoints are all so close together, it doesn't matter. Now for simplicity, we're going to work with the right endpoint approximations when we find area. So when you see Riemann sums, they almost always will use the right endpoint, and it's because it doesn't matter and it's the easiest one to use. The second note is that this limit requires a lot of work and simplification of the summation formula. So we would need to know how to get rid of that sum symbol in order to take the limit. We're not going to be focusing on taking these limits in this course, which is what I just said. But much like with derivatives, which are defined in terms of limits, we have an easier way to find the signed area between a function and the x-axis, and it's going to be using antiderivatives. And so in section 5.3, which is the fundamental theorem of calculus, we're going to be seeing this. So that's it for this section. Thanks for listening.